All right, let's dive right in. If you've spent any time at all around AI, you've definitely heard these four words thrown around: training, inference, algorithm, and model, right? And look, they get used interchangeably all the time, which can be, well, super confusing. But here's the thing: getting these terms straight isn't just about semantics, it's the key to understanding how AI actually works under the hood. So, what is the real deal here? I mean, is a model just a fancier name for an algorithm? Is inference basically the same thing as training? The answer is a huge no. And the difference is actually pretty simple, but also really important. It's all about separating the learning part of machine learning from the doing part. And trust me, understanding that distinction is crucial if you want to make smart choices when you're building with AI. Okay, to make this all crystal clear, we're going to use one simple analogy for this whole explainer: building a house. Seriously, that's it. We're going to start with the blueprints, then we'll actually build the thing, and finally, we'll move in and live in it. Just keep that idea in your head, because I promise it's going to make everything else just click. All right, first up, the blueprint. Let's tackle that really common confusion between an algorithm and a model. And in our house analogy, this is super simple. It's the difference between the blueprint and the actual building. So, what's an algorithm? Think of it as the process. It's the set of rules, the recipe you follow to create a model from data. In our analogy, it's not just the architect's blueprint, it's the blueprint plus all the engineering principles you need to actually construct the house. It's not the house, it's the instructions for how to build the house. The model, then, is the exact opposite. It's the output. It's the finished product. It's the specific, tangible house that you built by following that blueprint. It's the thing that holds all the knowledge the algorithm learned from the data. I mean, think about it. You can't live in a blueprint, right? But you can definitely live in the house. The blueprint is the algorithm. The house is the model. So let's just nail this down. Algorithm is the process, model is the output. Algorithm is the blueprint, model is the building. One is the procedure you follow to learn, and the other is the actual knowledge you learned, all packaged up and ready to go. Okay, now this is where it gets really cool, because this slide shows something that's a bit of a mind bender at first. Take a look. For an algorithm like linear regression, the process works hard to find a specific set of numbers, these coefficients, and that becomes the model. But now look at k-nearest neighbors. The algorithm is ridiculously simple. You just save all the training data. That's it. The model is the data. This is so brilliant because it shows a model isn't just one thing. It's a combination of the stored data and the little bit of code, the prediction algorithm, that knows what to do with that data. Okay, let's move on to our next pair of terms, the build. If the algorithm is the blueprint and the model is the building, then training versus inference is all about the action. It's the difference between actually constructing the house and then moving in and using it. So training is the heavy lifting. This is the building the house phase. You gather up a ton of high-quality data, you pick the right kind of architecture, and then you start feeding all that data into your algorithm. The whole point is to let it churn through the data, adjusting all its internal knobs and dials over and over again until it gets really, really good at what it's supposed to do. This is the super compute-intensive part, you know? It can literally take days or even weeks running on some seriously powerful computers. And then comes inference. This is showtime. It's runtime, when your perfectly trained model is put to work on brand new data it's never seen before. Back to our analogy, the house is built. A family moves in, a massive storm rolls through, and the house keeps them safe. That is inference. Every time your phone unlocks with your face or an email gets zapped into your spam folder, that's a model doing its inference job. This table just lays it all out so perfectly. I mean, look at the contrast. The purpose of training? To learn from data. Inference? To make predictions. Look at the duration. Training can take weeks. Inference happens in milliseconds. And the frequency is key. You train a model every once in a while, but you are using it for inference constantly, all the time. They are just fundamentally different jobs with completely different needs. Okay, so we've got the definitions down: algorithm, model, training, inference. But why does any of this really matter? Why should you care? Well, it turns out this distinction isn't just academic. It has absolutely massive implications for the real world. It all boils down to this one number, 10x. That's right. According to people who watch this stuff for a living, in the next few years, the amount of computer power needed for inference, for the doing part, could be 10 times more than what's needed for training. Think about that. The doing part of AI is about to completely dwarf the learning part in terms of pure scale.
And here's why. The compute needs are just worlds apart. Training, that's the brute force work. It needs these giant clusters of powerful GPUs all working together to just crunch massive amounts of data. But inference, that's a different game entirely. It's all about being fast, efficient, and having low latency. It needs to run in an instant, sometimes on a tiny chip inside your phone or your car. And this huge difference in what's needed is literally reshaping the entire chip industry.
And you see this pattern playing out everywhere. Look at healthcare. A model gets trained one time on thousands of medical images, but then it performs inference thousands, maybe tens of thousands of times a day, giving instant diagnoses for new patients. Or self-driving cars. They train on millions of miles of road data, but they use inference to make thousands of split-second decisions every single minute. The pattern is always the same. Train once, infer constantly.
So we've spent all this time establishing this really clean, neat separation between learning and doing, between training and inference. But what if that's just how we do it now? What if the next big step for AI is for it to act a little more like, well, a little more like us? This is such a cool idea. Think about our brains. For us, learning and doing are not two separate things. Every single time we see or hear or think something, every act of inference we perform, it literally changes the connections in our brain. Just a little bit. We are constantly learning, constantly updating in real time. Our internal models aren't static, they're alive. Now, of course, there are some really good practical reasons we separate them today. For one, it's just way more efficient. It also helps the model generalize better, so it doesn't get totally thrown off by every new thing it sees. And, maybe most importantly, it makes the model's behavior predictable and reproducible. You definitely want your medical AI to give the exact same diagnosis for the exact same scan every single time, right?
But it does leave us with this really mind-bending question for the future. Right now, we are masters at creating these static snapshots of intelligence. But what if the next great leap forward is an AI that completely blurs that line? A machine that learns as it lives, constantly updating itself with every new experience, every single act of inference, shaping itself through every interaction, just like we do. What would an AI like that even be capable of? You have to wonder, because that might just be the next frontier.